In this video, we're going to discuss the solutions for the midterm exam on linear algebra during the spring semester 2018. The midterm exam contains 5 problems on the following topics. So let's start with the first problem. The first problem is about the matrix operations. We're given the T matrices and we need to do the following operations with those matrices. So in the first part, in order to add the T matrices, we just need to add them component-wise. So that is why the A plus B is going to be equal to 2 plus 2, 1 plus 0, 3 plus 0, 0 plus minus 1 plus 1, 5 plus 3, minus 4 plus 5, 2 plus 1, 1 plus 0. So we obtain the following matrix. So in the second part, we need to multiply the T matrices, the A transpose. So A transpose is obtained by writing down the rows of this matrix as the columns of the new matrix. It can be written T, 1, 3, 0, minus 1, 5, minus 4, T, and 1. And we have to multiply this as a B, which is T, minus 1, 5, 0, 1, 1, 0, 3, 0. So it would be better for us to multiply these T matrices as a combination of columns of the first matrix using the coefficients from the columns of the second matrix, right? So let's do the combination. The first combination is we multiply the first column T, 1, and 3 to the T. We multiply the second column 0, minus 1, and 5 to the minus 1. And we multiply the last column minus 4, T, and 1 to the 5. And we need to obtain a vector which is going to be put on the first column of the resulting matrix. So it's going to be 4, T, 6, plus 0, 1, minus 5, plus minus 20, 10, and 5. So if we add these 3 vectors, we're going to obtain minus 16, 13, and 6. So I need to put this as the first column of the resulting matrix. And in order to obtain the second column, I need to use the following coefficients, right? So I need to multiply the 3 columns again to the 3 coefficients. So in this case, I see that I just need to add the T last columns. It is going to be minus 4, 1, and 6. And the last 3 numbers are going to tell me, so I just need to multiply the second column to the 3 and copy this as the last column of the resulting matrix. It's going to be 0, minus 3, and 15. And in the last part of the problem, so when you define the determinant of the B transpose, so again we're going to obtain the B transpose by writing down the rows of this matrix as the columns. So it's going to be 2, 0, 0, minus 1, 1, 3, 5, 1, 0. So we can find the determinant by going through one of the rows or one of the columns. So we can do, for example, find the determinant by going through the first column. So all the elements through the first column. So it's going to be, so I need to choose first of all the value T multiplied to the determinant of the matrix, which is obtained by eliminating this T, the row and the column where this T is located. It's going to be 1, 1, 3, and 0. So plus 0 multiplied to the determinant, which is obtained by eliminating the row and the column where it is located. It's going to be minus 1, 5, 3, and 0, plus the last 0 multiplied to the determinant of the matrix, which is obtained by eliminating the row and the column where the last 0 is located. It's going to be minus 5, 5, 1, and 1. So actually the last 2 determinants are equal to the 0. So the only thing which I have to obtain is this determinant, which is going to be 1 multiplied to the 0 minus 1 multiplied to the 3, which is going to be minus 3. And if I multiply this to the T, we obtain minus 6. The second problem is about the vector spaces of the matrices. So first of all, we need to find the column space. So the column space of the matrix is the span of the independent columns of the matrix. So in order to find the independent columns of the matrix A, we need to bring the matrix A to the reduced row echelon form. 1, 1, 2, 4, 3, 4, 2, 8, 0, 0, 2, 2. So again, we need to start from the first row, which is the first non-zero element, and this is going to be the pivot, and we need to eliminate all the elements below this. So first of all, I'm going to eliminate this 2, and in order to do this, we multiply the first row to the -3 and add this to the second. What we obtain is the following matrix. It's going to be 0, 1, -4, -4, 0, 0, 2, and 2. Okay, so now we need to go to the second row, right, and choose the first non-zero element and eliminate all the elements below this. They are already eliminated. And we need to go to the third row, and find the first non-zero element and eliminate all the elements below this. So this matrix is already in the row echelon form, and I've got the 3 pivots on this matrix. The first one is on the first row, second one is on the second row, and the third one is on the third row. So the first 3 columns of this matrix are independent, and the last column here is dependent, or the free column. So that is why we can write down the column space of the matrix as the linear combination of the first 3 columns, which are 1, 3, 0, 1, 4, 0, and 2, 2, 2. This is going to be the column space of the matrix. So in order to find the null space of the matrix, so we need to find the special solutions. The null space of the matrix, it's going to be the span of these special solutions. In order to do this, we need to bring the matrix to the reduced row echelon form. So let's just continue. So this part, when we did in the first part, was the Gauss elimination. We just need to continue to bring this matrix to the reduced row echelon form, and we can do this by eliminating all the elements above the pivots, or we can try to do this right immediately from here. So let me write down the system of linear equations, which is going to be x1 plus x2 plus tx3 is equal to the 4 xt minus 4x3, the last column is about the variable, right, plus 4x4 is equal to the 0, xt minus 4x3 minus 4x4 is equal to the 0, x3 multiplied to the 2 plus 2x4 is equal to the 0. So since the last column is the free variable, its corresponding variable x4 is also going to be the free variable. So since there is one free column, we're going to have only one special solution, and we can obtain this by solving this system of linear equations, where we assign the value for the free variable to be equal to the 1. So if I substitute x4 to be equal to the 1, I can find the special solutions. So from the last equation, what we obtain as here is tx3 plus 2x4, which is 1, is equal to the 0. From here, we obtain that x3 is equal to minus 1. So we need to substitute x4 and x3 to the second equation. It's going to be xt minus 4 multiplied to the minus 1, minus 4 multiplied to the 1 is equal to the 0. From here we obtain that xt is equal to the 0, and if we substitute xt, x3, and x4 to the first equation, we can find x1. It's going to be x1 plus 0 plus 2 multiplied to the minus 1 plus 4 multiplied to the 1. It is going to be equal to the 0, and from here we obtain that x1 is equal to minus 2. So the special solution for the system, it's going to be equal to the vector with the components minus 2, 0, minus 1, and 1. And the null space of this matrix A is the all possible linear combinations of this vector. In the last part of this problem, we need to find the complete solutions to the system Ax is equal to the b. In order to do this, we need to bring the matrix, augmented matrix, to the reduced echelon form. So let's bring the augmented matrix to the reduced echelon form. So which is going to be 1, 1, 2, 4, 1, 3, 4, 2, 8, 4, 0, 0, 2, 2, 0. Again, we're going to make the similar operations. We multiply the first row to the minus 3 and add this to the second. And what we're going to obtain is 1, 1, 2, 4, 1, 0, 1, minus 4, 1, 0, 0, 2, 2, 0. So this matrix is already in the reduced row echelon form. And we can see from this matrix that the first 3 columns are the pivot columns, and the column number 4 is the free column. So that is why the x4, which corresponds to the fourth column, is going to be the free variable. And in order to find a particular solution, we need to set this to be equal to the 0 and solve the system Rx is equal to the D, where the R matrix is this matrix, row echelon form of the A, and D is this vector which we obtained when we did the row echelon, when we did the row eliminations. So let's write down the system. It's going to be x1 plus x2 plus 2x3 plus 4x4 is equal to the 1, x2 minus 4x3 minus 4x4 is equal to the 1, 2x3 plus 2x4 is equal to the 0. So if I substitute x4 to be equal to the 0 to the last equation, we obtain that x3 is also equal to the 0. Now if we substitute x4 to be equal to the 0 and x3 is equal to the 0, we obtain that x2 is equal to the 1. If we substitute the 1 for the x2, 0 for the x3, and 0 for the x4, we obtain that x1 is also equal to the 0. So the particular solution for the system is going to be equal to the 0, 1, 0, and 0. And in order to find the complete solution, actually, what we can do is we can write down the particular solution plus the span of the spatial solutions, which is going to be some parameter t multiplied to the spatial solution. So we can write down the complete solution in the form of 0, 1, 0, 0 plus minus 2, 0, minus 1, and 1 multiplied to some constant for all values of this constant from the set of real numbers. So in the problem number 3, we need to find the LU decomposition of the matrix A, and just using the LU decomposition, we can solve the system of linear equations by just doing the backward substitution and forward substitution. So let's find the LU decomposition of this matrix A. In order to do this, we need to eliminate all these 3 elements below the diagonal, so that the matrix becomes the upper triangular. So in order to bring this matrix to the upper triangular form, we need to multiply the matrix to the elimination matrices. So the first matrix is going to multiply the first row to the 1 and adding this to the second row, 6 minus 4 and 0. So this elimination matrix is going to be the first 1, 0, 0. It keeps the first row as it is. It keeps the last row also as it is, and it is going to add the first row to the second by multiplying the first row to the 1, second row to the 1. We can do this operation. So if we multiply this matrix, what we're going to obtain is 3 minus 7 minus 2. Now if we multiply all the elements of the first row to the 1 and add this to the second, we're going to obtain 0, minus 2, and minus 1. And the last row is going to be unchanged again. So this matrix here is E to 1. So now we need to multiply the last matrix, 3 minus 7 minus 2, 0 minus 2 minus 1, 6 minus 4 and 0, to the elimination matrix E3, 1, because we're going to obtain the 6. So we can obtain the 6 by keeping the first two rows as they are, and by multiplying the first row to the minus 2 and adding this to the last row, we'll eliminate the 6. It's going to be minus 2 multiplied to the first row, second row is multiplied to the 0, and the third row is multiplied to the 1. So what we're going to obtain is 3 minus 7 minus 2, 0 minus 2 minus 1, 0, 10, and 4. And in the last step, we're going to eliminate this 10. So we can do this by multiplying the matrix to the elimination matrix E32. So which is going to be obtained. So I need to use this pivot now in order to eliminate this. If we multiply the second row to the 5 and add this to the last row, we're going to eliminate this 10. So we need to keep the first two rows as they are. So what we're going to obtain here is 3 minus 7 minus 2, 0, 2 was the minus, minus 1, 0, 0, minus 1. So what we need to do is now is we obtain the U matrix here. So by multiplying the A to the E1, E31, E32, we obtain the upper triangular matrix. In order to find the lower triangular matrix, we need to put the three matrices to the right hand side part, and we can do this in this way: E32, E31, E21, and its inverse multiplied to the U. So if you open up the multiplication and its inverse, it can be written as E1 its inverse multiplied to the E31 and its inverse multiplied to the E32 and its inverse multiplied to the U. So the multiplication of the three numbers is going to give us the L matrix. So fortunately, finding the inverse of the elimination matrices are easy. We just need to change the sign of the element which is below the diagonal. So the inverse of the E1, in this case, it's going to be 1, 0, 0, minus 1, 1, 0, 0, 0, 1. The inverse of the E31, it's going to be it's obtained by just changing the sign of this element, which is going to be 1, 0, 0, 0, 1, 0, 2, 0, 1. And the inverse of the E32, it's obtained by changing the sign of this element below the diagonal, which is going to be 1, 0, 0, 0, 1, 0, 0, minus 5, and 1. So again, we can multiply the three matrices by combining the rows or the columns of the matrices. So in the first case, we can combine the rows of the second matrix, right? So using the coefficients from the rows of the first matrix. So what we're going to do is we multiply the first row to the 1, second row to the 0, third row to the 0. What we're going to obtain is simply the first row. In the second row, it is given that we need to multiply the first row to the minus 1 and add this to the second row. It's going to be minus 1, 1, and 0. And the last row is kept as it is. So we need to multiply this to the last matrix, which is 1, 0, 0, 0, 1, 0, 0, minus 5, and 1. So in this case, it is better for us to combine the columns of the first matrix using the coefficients from the columns of the second matrix. So now we need to keep the first column as it is. So in order to obtain the second column, we multiply the third column to the minus 5 and add this to the second one, which is going to be 0, 1, and minus 5. And the last column is kept as it is. So this is going to be our L matrix. So we obtain the U matrix here, and we also obtained the L matrix here. So in the third part of this equation, of this problem, what we need to do is we need to solve the system of linear equations Ax is equal to ZB using its LU decomposition. Basically, we're going to split the system. We can first of all write down the A as the LU, X is equal to ZB, and we're going to split this to T systems into T parts. So if we just denote this U multiplied to the X to the Y, so the system becomes in the form of U X is equal to the Y, and the the system here, it also becomes L multiplied to the y is equal to the b. So what we're going to do is we're going to solve the system first and substitute the y to the first system, and we can obtain the x. So our L matrix was 1, 0, 0, minus 1, 1, 0, 2, minus 5, and 1. We have to multiply this to some unknown vector y, y1, y2, y3, and this should be equal to the b vector, which is given as minus 7, 5, and 2. And we can obtain the solution by doing one-time forward substitution. So y1 is going to be equal to the minus 7. So now we need to substitute y1 to the second equation, basically. Minus 1 multiplied to the y1, which is minus 7, which is going to be just plus 1 multiplied to the y2 is equal to the 5. From here we obtain that the y2 is equal to minus 2. And if I substitute the y2 and y1 for the first equation, for the third equation, which is 2 multiplied to the y1, which is minus 7, minus 5 multiplied to the y2, which is minus 2, plus y3 is equal to the 2. So it's going to be minus 14 plus 10. So if the minus 4 goes to the right, we obtain that y3 is equal to 6. So we find out the y vector, and we can find the x vector by just solving this equation. So the U matrix was 3 minus 7 minus 2, 0 minus 2 minus 1, 0, 0 minus 1. If we multiply this to the vector x1, x2, and x3, it should be equal to the y vector, which is minus 7, minus 2, and 6. So we can solve the system by doing one-time backward substitution. So the last equation tells us that minus x3 is equal to the 6, or x3 is equal to the minus 6. So we can substitute this to the second equation, which is minus 2 multiplied to x2 minus 1 multiplied to x3, which is minus 6. It should be equal to the minus 2. And from here we obtain that x2 is equal to 4. So now we need to substitute x3 and x2 to the first equation, which is 3 multiplied to x1, minus 7 multiplied to x2, which is 4, minus 2 multiplied to x3, which is minus 6, is equal to the minus 7. So what we obtain for the x1 is equal to 3. So the vector x is going to have the 3 components, x1, x2, and x3, which is 3, 4, and minus 6. The problem number 4 is about the solvability of the system of linear equations. So we need to find out such a matrix A so that this system has no solution. So the system has no solution, Ax is equal to the B has no solution, if the vector B is not in the column space of the matrix A. For example, I can choose the column space of the matrix A as some line, which might be 1, 0 line, right? And I can choose the second column also as 1, 0, and this is going to be just a line, which is this line, with the components 1 and 1. And this vector 1 and 2 is not in this line, so this vector is here, with the components 1 and 2. And it is impossible to obtain this vector, red vector 1 and 2, by just scaling this vector 1 and 1. So if I multiply this to the x1 and x2 is equal to the 1 and 2, it doesn't have the solution. So the system of linear equations Ax is equal to the B has unique solution if the matrix A is invertible. So I can choose any matrix, 2 by 2 matrix, whose determinant is not equal to the 0, for example, 1, 2, 1, 0. In this case, determinant is not equal to the 0, so that is why the matrix A is invertible, and the system of linear equations Ax is equal to the B has the unique solution. So if I want that the system has infinitely many solutions, so I need to choose the columns of the first matrix as as dependent columns in a way that the column B, the right hand side part B, is lying in the column space of the A. So I need to choose the columns of the first matrix A as dependent so that this B is in the column space. So for example, I can choose the columns 1, 2, and 1, 2. So geometrically, so I'm choosing the column space of this matrix A as this vector 1 and 2, or the line along this vector, and obviously I can obtain this vector B, right, in infinitely many ways, because the column space is here, all the vectors along this line. The last problem, we need to find the inverse of the matrix using the Gauss-Jordan elimination. The idea of the algorithm is that we need to put the matrix in the identity matrix, and by applying the Gauss-Jordan elimination, we need to bring this matrix to the form of I and A inverse. So let's start doing this. So we need to write down the matrix itself first of all, and then later on we need to write down the identity matrix just after this matrix. So we need to start reducing this. So we see that this matrix is already in the row echelon form. So it means that if I choose the pivots on the first, second, and the third rows, all the elements below them are equal to the 0. So what I have to do is I need to eliminate the elements above these 2 pivots. So in the first step, we're going to eliminate this 2. So we can do this by multiplying the third row to the minus 2. And adding this to the first one allows me to eliminate this 2 on the first row. So please note that in this case, I need to keep the last 2 rows as they are. And now I need to multiply all the elements on the third row to the minus 2 and add this to the first one, which is going to be 2, 1, 2, 0, 1, 0, minus 2. So now we need to eliminate this 2 in order to bring this matrix to the identity form. In order to do this, we're going to multiply the second row now to the minus 2 and add this to the first row. So please note that I'm not going to change the first 2, the last 2 rows. It's going to be 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1. Now if I multiply all the elements on the second row to the minus 2 and add this to the first row, we're going to obtain 1, 0, 0, 1, minus 2, and minus 2. So we'll bring this augmented matrix to the form when we have the identity matrix on the left hand side, and this matrix on the right hand side is going to be the inverse of this matrix. So we can check whether we found a proper inverse by multiplying the A matrix, which is 1, 2, 2, 0, 1, 0, 0, 0, 1, to its inverse, which we found, which is 1, minus 2, minus 2, 0, 1, 0, 0, 0, 1. So it is obvious that the last 2 rows of this matrix are equal to the 0, 1, 0, 0, 0, 1. Right? So I just need to check the first row of this matrix. So if I multiply the first row to the first column, I'm going to obtain 1. If I multiply the first row to the second column, we're going to obtain 1 multiplied as a minus 2, 2 multiplied as a 1, which is 0. The first row multiplied to the last row is going to be 1 multiplied as a minus 2, and 2 multiplied as a 1, which is going to be 0. And the second row and the third row are equal to 0, 1, 0, 0, 0, 1. So indeed this matrix is the inverse of the A.